Section 11.7, Cylindrical and Spherical Coordinates. In this section, we will talk about how to convert rectangular coordinates to cylindrical and to spherical, and then all in between combinations as such. Cylindrical coordinates, you recall from Calculus 2, is the same thing as polar coordinates. And for the idea of cylindrical coordinates, we have a point that is set to match up with the point that's in rectangular coordinates. So for the rectangular coordinates, you have x, y, and z. I guess if I could circle correctly, we'll be all right. And then its corresponding point in polar coordinates for the xy plane, cylindrical for the xyz plane, or the space coordinate system. So for cylindrical, we take the radius, we take the angle that's between the x-axis and the resultant, or the radius, and then z to go upstairs. So the radius is in consideration for cylindrical coordinates, the side of x, and then z. And so from there we have some point, we say P, and we're able to construct P in the space coordinate using these, whether it's rectangular or cylindrical. What corresponds if you extract this so-called right triangle from the diagram up there, and so from there you build all of the relationships, that is that tan theta is equal to y over x. And if you were solving for theta, theta is equal to tan inverse of y over x. From this right triangle, we understand, according to Pythagorean, that x squared plus y squared is equal to r squared. Also, we can build cosine theta is equal to x divided by r, and that implies then that x is equal to r times cosine theta. Likewise, sine theta is y over r, and that implies that y is equal to r sine theta. And for the coordinate system here for cylindrical, so we have the component of r theta, and then z just comes back over from the rectangular system. Secondly, we deal with how to convert from rectangular, cylindrical to spherical. And so for the spherical coordinate system, we have the definition that it's some point P, the same point P, that is from the previous conversation. Here we relate the so-called resultant in space, the same thing that r does in the xy plane, rho now does in space. trying to make sure we had a picture of that, and we do. So rho is the distance between P and the origin, and now we have theta, which is the same angle between X and R in the XY plane. And then the second angle, phi, is the angle in space between the z-axis and the resultant rho. Now, if you wanted to kind of pull that out and look at the right triangle, we can build all of these relationships here. So here is phi. Won't be able to stick that guy in there all the way, so this angle here is phi. Don't know why I want to write theta. So we have phi here. This is z. And then this is r. And then we have rho. Okay. So what we're doing is looking at this triangle here, and I know it looks kind of slanted, but that's where the so-called right angle is. This is R. This is Z. We're creating here a parallelogram. So from this right triangle, we can build all the very neat consequences that we want. So say, for example, if you look at sine of phi, so that's going to be the opposite over the hypotenuse, so r over rho. Well, that kind of helps us neatly extract what r would be. So r is rho times sine phi. That's a pretty messed up looking phi. Let's change the color. Cosine phi, z over rho. That implies that z is equal to rho times cosine phi. And now, again, let's get the tangent, and then I'll look at what I was about to say. Tangent of phi is r over z. Now, to get the angle, it's a little bit better to use the cosine. Let's see. So cosine phi is equal to z over rho, and this implies that rho is equal to cosine inverse of z over rho. Now, why do we use cosine? It's because we want to relate the quantities back to rectangular coordinates. And so what I was going to say earlier is that when you look at this right triangle, if you use the Pythagorean theorem, we have, we have z squared plus r squared is equal to rho squared. Now, r squared is x squared plus y squared. So I'm going to write the r squared first, and the terms here will be x squared and y squared. So x squared plus y squared plus z squared is equal to rho squared. So from there, you can extract what rho is. Rho is equal to x squared plus y squared plus z squared. So if that be the case, yes, cosine phi is equal to z all over rho, and rho is the square root of x squared plus y squared plus z squared. So it's somewhat good to be able to see how they build all of these consequences by just extracting from the diagram. Now, what about x? You recall that x from rectangular to cylindrical is equal to r times cosine theta, not phi. But we said that r is equal to rho times sine phi. So x is equal to r, which is rho times sine phi times cosine theta. Likewise with y is equal to r sine theta, and r again is equal to rho sine phi and then times sine theta. So I think with that you should be good to go with the conversion. I'll come back in just a moment and we'll talk about how to convert all of these consequences. Thank you.